quick walkthrough through step assignment number 8. The question was this here, quite a short question. You need to show that the equation of any circle passing through the points of intersection of this ellipse and this ellipse can be written in this form. Now, you can't do this in a step exam, but what I want to do is I just want to frame what this question is actually talking about, because it's quite difficult to understand just by reading it. What it's saying is you have an ellipse here, and you have an ellipse here, and now I can use a graphing calculator to plot these. Now you can't, but I just want to show you what this means. You have two ellipses. I honestly don't know which is which, and they have points of intersection, which are clearly here and here. And we're talking about, you're trying to show that the equation of any circle that passes through these two intersection points obeys this law. So we're just talking about circles that pass through those two intersection points, whether they look like this or this or this, right? So we're just looking for some rule that apparently all of these red circles follow because they go through these two intersection points, right? So that's what the question is talking about. Now let's get to it. Now again, you can't graph this, but let's get to it. So the first thing I would do, now the key points were the intersections, right? That's all we need. So let's look at the intersections of these two curves here. Now to do that, what I'm going to do, there's tons of ways you could have done it, but I'm going to isolate the 2y squared here by taking away this from both sides, isolate the 16y squared there by taking away that from both sides, and then if I multiply this whole equation by 8, I think I end up with this. And this is good because now I have two equations or two ways of writing 16y squared. So therefore this thing here must be equal to that thing there. And this is great because now it's just an equation in x, and I know I can solve that. And in step questions like this, be super careful. Do not mess up algebra like this. That's x plus 2 times x plus 2. That's x minus 1 times x minus 1. Don't involve the x until you're happy that you've expanded. Sorry, don't involve the 8 until you're happy you've expanded this properly. Eventually you end up with this. Be careful of these negatives as well. And that negative in particular swaps all these signs. So do not make mistakes on that. Be really careful. At this point, add 9 squared to both sides. Take away 18x, sort out the numbers, and you end up with this. You can complete the square here, or you can use the formula, or you can notice that 48 and 2 are your friends, and you can get the answers of 2 and 48 here. Okay, so those are the x coordinates of the intersections of these two ellipses. So let's find the y coordinates. How I'm going to do that is I'm going to just take the slightly more friendly looking ellipse, and I'm going to substitute in my 2x coordinates that I have so far. So let's put 2 in first, and we get 2 plus 2 is 4, squared is 16. Take it away from both sides, divide by 2. Be careful here, when you square root, you get a plus and a minus, which means our 2 points of intersection that this point creates are 2, 1, and 2, minus 1. We write this one, so we put in 48 into here, add that to make 50, square to make 2,500, take away that from both sides. Some of you might be able to see where this is going now, divide by 2, and unfortunately this doesn't have any solutions. Not any real solutions anyway. So we're going to say no solutions there. And so our only points of intersection are these two here, which is good if you already graphed this because you cheated and you saw that they were at 2, 1, and 2, minus 1. It's good that I've confirmed that just using algebra. So I didn't really have to graph this, but it's nice that it does seem to work. Okay, so I'm on the right track because I found my two intersections. Now, what we notice here, like I said before, is the ellipses are irrelevant. I don't care about the ellipses. I just care about the intersections of them because that's what these circles are going to be doing, right? It's just about the intersection, the 2, 1, the 2, minus 1. And apparently all of these different circles obey some law, which I'm about to find out, which is actually this one. I already know it, but I'm about to prove it. All these circles obey this kind of rule. So what's the equation of a circle? Well, it's this with center A, B, radius R. And now I've got the 2 points that the circle goes through. I know the circle goes through 2, 1, and 2, minus 1. So let's substitute both of those into this equation here. So let's put 2, 1 in first, 2 and 1. Expand that out really carefully. Check that I've got this right, please. Then substitute 2 and minus 1 in. Expand that out really carefully. Be super careful of all of this negative stuff. But I hope you get this. And now if I just slot this one underneath this one and take away, 4 take away 4 is 0. Minus 4a take away minus 4 is 0. That take away that is 0. 0. That take away that is actually minus 4b, but that's 0 and that's 0. So minus 4b is 0, which of course means that b is 0, which is great, because that eliminates one of these unknowns that I didn't really want here. So I know b is 0, which means I can update my formula to be this. And now I just need to look for a and r. Well, let's go back to that blue equation that I had on the previous slide, but I know b is 0 now. So let's get rid of all this. It must be this. And now r squared is right here. So I'm just going to put r squared, put what I know r squared to be straight into there. And that's great because that just forms an equation with x, y, and a, which is exactly what's on up here. So let's expand this out again really carefully. That's going to make a positive, remember, just there. Cancel the a squared, so look how beautiful this is. 4 plus 1 is 5, and we arrive at the end of the question. And that is the entire step question. So really well if you got that. I just want to take a minute or so just to talk about an alternative way you could have found b. Remember, I found b is 0 by doing algebra, because I am an algebra man through and through. I'll do it all day. So I found b was 0 by algebra, but you can also do it using some geometry rules. So here was the circle that we were talking about. Or one of them. We were talking about all the circles that go through these 2 points, remember. So here's one of the circles we were talking about. Well, let's put the chord down between 2, 1 and 2 minus 1. And now we have a theorem, a circle theorem, that says the radius of a circle bisects any chord of the circle and is perpendicular to it. So where is the bisecting point of this chord here? Well, it's clearly at 2, 0. Right? Because it's 1 up and 1 down from there. So it's clearly at 2, 0. So the radius not only goes through this point, because it bisects it, but it's also perpendicular. Now this chord is a vertical line because the x coordinates are both 2. So perpendicular is a horizontal line, which means the radius looks a bit like this, which means that the radius, the center of the circle, if the radius is just going along like this, the center of the circle is on the x-axis, which means the y-coordinate of the center is 0. It's like some point a0, which means that when we went into our formula for the circle, the y-coordinate of the center is 0, which means we can just update it to be this, which is what I did via algebra. But you can do it via geometry as well, which is really nice. And then to complete this, you would then do some algebra, just like I did. But yeah, really well done if you got that question.